I'd like to thank organizers. And of course, I'm not working on the liquid crystal, but I'm working on related model. Okay, so this is one of the related model, so-called the Cucker-Smale-Navier-Stokes model, coupled with bonding force and noises and fluid. Right, hold. So here's a brief outline of my talk. So I'm going to talk about 5C, okay? The first C, Cucker-Smale model. Second C is coupling with bonding force, coupling with noise, coupling with the fluids, and conclusion, okay? All right, so I found out several pictures from Google. So you see the swarming of fishes is called the milling phenomena, or flocking of birds, or herding of cows, etc. So in this talk, I'm going to use flocking to denote this kind of phenomena. So it's alignment in the velocity, roughly speaking. So that's the relation between orientation in liquid crystal. So here is the alignment in the velocity. So here, the ambitious question that you can ask for this biological model is, how can these collective motions emerge from possibly simple rules, okay? Or if I can answer this question, then I'm so happy, but at this moment, we don't know, okay? But we can imitate somehow. So the flocking phenomena is basically you have a disordered multi-agent system for some communication between agent, called self-propelled particles, and this order emerges from this disordered state. Okay, so the question is, what kind of mechanism to make this disordered state into ordered state? So again, the relation between the liquid crystal and flocking is this. Liquid crystal, you are interested in the emergence of orientation order. Now I'm interested in the emergence of velocity alignment. Okay, here the velocity alignment in the asymptotic sense. Okay, time asymptotically. So the recent model for this flocking is proposed by these two mathematicians. Sorry for this low resolution. It's Philip Cucker from City University, Hong Kong, and his colleague Steve Seungyeal, again from the same university. Years ago, like 2007, they introduced the following simple ODE system. So xi is the position of ice agent, vi is the velocity of ice agent, and here we assume that all agents have the same mass, say 1. Then clearly the velocity of the derivative of position is the velocity, and this is a ma part, acceleration times the mass is 1, then is given by some force. They just use this kind of coupling in the linear coupling in the velocity multiplied by some weight. I call the communication weight. So why? So if you think, okay, so for example, if you consider one-dimensional particle, okay, so the particle just move along the line, and I is just let's suppose it's your velocity. If your neighbor's velocity is larger than your velocity, then this part is positive, and here we assume that the weight is positive. Therefore, the contribution due to the fast particle gives you positive acceleration. So that means if your neighbor has a larger velocity, then you need to accelerate to have the same velocity. On the other hand, if your neighbor's velocity is slower than you, that means this acceleration is negative, then you have to decelerate your velocity to have the same velocity with your neighbors. Okay, so the positive, the attractive coupling is hidden in this mechanism. Okay. And in Cucker-Smale's paper, they use this algebraically decaying communication rate. This somehow makes sense because if the relative distance between two particles is larger, then the communication somehow will be smaller. Okay, and also to avoid the singularity, when two agents have the same position, they just regularize by adding some constant here. Okay, so I'll go back to that question later. And so what they prove, basically what they prove is, if depending on beta, for example, here remember 2 beta is the decay rate. So 2 beta is larger than 1. That means this guy decay faster. It's called short range interaction. Then you have a condition of flocking depending on your initial configuration. If 2 beta smaller than 1, that means you have a long range interaction. Then independent of your initial configuration, this simple model exhibit flocking all the time. Okay, so you have some like a phase transition phenomena, something like that, depending on the decay rate, 2 beta equal to 1. Okay, so in last few years, there are many works relate to this model. Okay. All right. So the easy solution that you can think of, say all particles have the same velocity, say vi equal to vj, then this term vanish. So you can find easy solution like so-called flocking solution. So it's a translation motion. Okay. So certainly depending on your initial position, you have infinite number of the solutions, simple solutions. And also this V infinity, actually you can calculate from the initial configuration, because you see this guy is a translation invariant. So if you add some constant here, it doesn't change. Therefore this guy, and also the total momentum, so this guy has one conserved quantity, so-called total momentum. If you add with respect to I, then you have a odd here, you have a even here, symmetric. So this guy vanish. So the total momentum is conserved. Therefore, your asymptotic velocity will be the average velocity of initial velocities. Okay. So now, then this model has one simple solution. However, has a lot of defect. Okay, when you apply this model to real situation, the first defect is that cannot avoid collisions, because here we basically assume that the agent is a point agent. Okay, so they can collide. Collision means they have the same position at given time, so they can avoid the collision. And also certainly has too many equilibria. You see, depending on your initial configuration, every translation motion will be the solution. Okay, so too many is not good also, and also cannot describe the milling phenomena. For example, this is called milling phenomena of fish. So this rolling. Unfortunately, the Cucker-Smale model as it is cannot describe this phenomena. These kind of things that I'm going to address today. Okay, how to modify, how to describe this phenomena, and then also I have one of the motivation also that I have is a relation with the statistical mechanics model, so-called ChromTomado. Okay, this is a Japanese physicist. Chromoto. So in 1975, he introduced this simple phase model. Here, theta I is the for example, if you have rotors, okay, so point rotors moving along the circle, let's say the i's rotor, let's denote set I to be the phase of this rotor, then the Kumamoto proposed this simple model, so-called Kumamoto model. Okay, in the statistical physics, this Kumamoto model is the prototype model for synchronization. I would say most statistical physicists working on this synchronization use this model. Okay. All right. So this is a first order model. Again, but the Cucker-Smale model is second order model, right? So if you just differentiate this first order model, then you'll get the second order model. It turns out this Cucker-Smale model and Kumamoto model, after you differentiate once, then you see certainly similarity between this Cucker-Smale model and Kumamoto model. For example, zeta I, this omega I is called frequency. It's a phase velocity. So you see. So the only difference is here, the psi. We assume that psi to be non-negative, but you see, if you see here, the cosine can be negative. However, this phase model is on the circle, so the repulsion is basically another kind of attraction. Okay, so somehow you can develop some unified theory between this Fracking model and this Kumamoto synchronization model. So okay, so let me, as I told you, I'm going to address three things. The first is avoid collision. The second thing is the Cucker-Smale model has lots of equilibria, but when you apply in real situation, you don't want to have infinite many solution. Okay, so you need to have a certain configuration, the configuration formation. So my first topic is the joint work with engineers in aeronautic department in my university. So it's coupling with bonding force. Okay, so basically we want to do this in future. You are air show, because sometimes we often hear that the airplanes collide each other, and this, that kind of accident happened recently in Korea also. So, okay, so I want to describe how to avoid collisions and formation control like this. Okay. So here's a simple theorem. It's not the theorem example. The collision can occur for the Cucker-Smale model for some initial configurations. So, for example, you have two particles, okay? So, then the Cucker-Smale model with this just with this simple communication weight is called the all-to-all case. It's just a linear system, and if you consider the difference x and v, this four equation just becomes two equation. Okay, so x is the relative position, v is the relative velocity. All right, this is so you can solve explicitly, right? Because it's decoupled. So, for example, x naught is positive. So you have x1, you have x2, you have x1. Then the velocity, this one is slower than this one. Then the coupling strength K is smaller than this one. Then by direct calculation, you may have a blow up. You may have a collision at this time. Okay. Of course, if the coupling is not that small, it's not that small, or if coupling is larger, then before these two particles collide, they reach the equilibrium state. So you can avoid the collision. Okay, so okay, all right. So certainly easy, clear why you need to avoid the collision. All right. So the collision avoidance for the Cucker-Smale model. So the previous approach by Cucker and his former student Dong, they add this original Cucker-Smale model. They add some collision avoiding mechanism here. All right, but okay. So here is the simple observation, because the first thing that I want to do is I don't want to add some new mechanism. Instead, I allow psi to be singular. For example, in original Cucker-Smale model, you have a regular communication weight, right? Because you add the 1 in the denominator. But if you allow like 1 over r to the gamma, like usual, the inversely proportional potential, then when r goes to 0, then the force becomes infinity, right? So this singular potential singular communication might prevent the collision. Okay, so for example, we consider the simple situation. You allow the singular kernel psi to be singular in this sense. Okay, so as goes to 0, this guy goes to infinity, then goes to 0, and like when s equals close to 0, you have a non-integrability condition. Suppose we have this kind of singular kernel. Okay, now let's go back to this just two-particle system on the line. Okay, so again, you consider these differences. Then you have that. You just integrate, because this guy is separable, so you can integrate like this, right? The usual ODE trick, you divide, right? Because you multiply dt, and v dt is a dx, so you can integrate this guy. So now, and so here is the proposition. So singularity can avoid collision for certain case. So from here, you can use the standard energy method. So you multiply v and integrate, and then what you can see here is the magnitude of relative velocity cannot increase. It's a contraction. Okay, just by using this energy method here. Let's suppose there is a collision, finite time collision between the agent. Okay, that means in finite time the relative distance becomes 0. So x t star equal to 0. Now from this relationship, okay, just from that relationship, we know that the right hand side is always finite, because this magnitude of this guy cannot increase in time. But when you plug in t approach to t star, okay, that means this guy approach to 0, then by our condition the psi, the integral becomes infinity. So therefore you have a contradiction. Okay, so for this two-particle system, the singularity in the communication can prevent the collision. Unfortunately, I cannot do it for general system. General, let's say the agent number is larger than 2. I have still problem. Then you can do something else. The first, okay, even the communication weight is singular. If you restrict your initial configuration, then you might have a collision-free solution. Okay, that's one possibility. Or the second possibility is add something new new mechanism in the original model to avoid the collision. On the other hand, achieve the formation control. Okay, so I can do two direction here. So the first story that I'm going to tell you is find out admissible initial configuration leading to collision-free solutions. Okay, so in order to do that, I introduce this kind of functionals, say relative distance, relative velocity, the minimum of relative positions, etc. Okay, so I also define this x sub m to be this one. Maybe I'm too fast. Oops. Oh, just a second. Okay, so now here's a theorem that you can prove initially the minimum distance defined here. Okay, if you give me the initial data, then you can determine this quantity and this quantity, and the precise given this x sub m is completely determined by initial configuration. Okay, just give me the initial data, then you can determine x sub m because precise given. Okay, so initially this quantity is positive, then you can prove that in time this quantity always positive. So, and also the relative velocity, the magnitude of relative velocity goes to 0. Okay, so in order to prove this, you can use some kind of Lyapunov function approach that I'm not going to talk here. And so here's a love thing, because if you just take this time derivative of this xij, then you have this estimate. This estimate gives you this estimate. So as long as this guy is large, this guy always bounded below by some positive quantity. Okay, that's the idea. As long as this guy is large, then you can bound below by some positive quantity here. The second story that I'm going to do, I'm going to add some new mechanism to the original Cucker-Smale model to avoid the collision and to get some desired formation control. Okay, so what kind of terms that we need to add? Here R is the you have a point particle, so this big circle on the center you have the particle located. Okay, so R is the desired kind of range to avoid the collision. So if you have a two particle, then the relative distance between two particles is exactly 2r, okay, which is the radius of the circle. So based on some heuristic argument, it's not the formula. It's just you can do this systematically. You can derive a new mechanism to account for the bonding force between the particles. Okay, looks terrible. We have so complicated terms here, but one thing that you need to note is, again, this quantity also is anti-symmetric with respect to the change of I and j, because if we change I and j, we have this kind of cubic term here, so it's non-symmetric. Also, this guy also has a translation invariant. Okay, so if we add some constant both here, it doesn't change. So therefore, if without loss of generality, you can assume that the sum of the xi equal to 0, sum of vi equal to 0, because otherwise you can subtract the average quantity from the beginning. You work on the fluctuation around its average quantities. Okay, Fortunately, this complicated system will have some kind of energy. The first thing that you can try is the kinetic energy. Okay, it's given, right? It's nothing argue about this. But how to define kind of potential energy or some other kind of free energy, that depends on trial and error. So I tried many things and then finally found out kind of this potential energy. I call configuration energy. So if you ignore R, this is a distance square, which is the harmonic potential. Okay. So if you add this kinetic energy plus this configuration energy as of course this kind of free energy, then this quantity satisfies the energy estimate. This P is a non-negative quantity, is defined here. So this E over T is non-increasing along this flow. Okay. Now, if you do some MATLAB simulation, then you can show a nice picture like this. So, because we propose this model, and basically we want to show that model avoid the collision. Okay. So, the first thing that we did is, if initial energy is sufficiently small compared to this number, this K2 is the coupling strength here, N is the number of agents, R is the desired avoidance range. Then you can prove that if initial energy is small enough, then you can prove that there is no total collapse in any finite time. That means every particle cannot collide at each one point. Of course, that's not what we want to do. We want to do more. Even two particles cannot collide at single point in finite time. But unfortunately, at that time, we couldn't prove that. And later on, we introduce this kind of functional E sub P to defined by the sum of magnitude of this guy. You see what this guy means. Basically, because what we expect as t goes infinity, this acceleration approach to zero, so that the configuration reach the steady state. That means somehow we expect these three terms goes to zero. So if you set this guy equal to zero, then you arrive this quantity. Okay. So, and this quantity, this functional, is a priori is bounded by energy. The somehow interesting on this functional is, again, the same smallness assumption on initial energy. What you can prove, kind of a Hanach type estimate. So the minimum relative distance bound the maximal relative distance. Okay. So once you proved this estimate, then you can prove collision, no collision. Why? Because before what we proved, under this assumption, we show that there is no one-point collapse. Let's suppose two agents collide in finite time at some point. That means this minimum distance becomes zero. That means maximum distance also becomes zero. Therefore, you have a finite time collapse, one single point collapse. But we prove that that cannot happen. So therefore, there is no one-point collapse. So this model, at least for the smallest assumption like this, you can avoid collision. Okay, the second topic that is the coupling with noise. This is joint work with my former student, Dr. An. Suppose we have a Cucker-Smale model. Sometimes this communication weight can be stochastic. That means this communication weight can be a sum of the deterministic part plus the noise part. Okay? Yeah. So here I took the white noise here. You plug into here. Then you have a deterministic part plus the noise part. Okay. By some simplifying assumptions, this noise stochastic perturbed model becomes like this system of SDE. What you can prove, again, fortunately, this one also the total momentum is conserved. So, okay, let me skip some of these. So what you can prove is you can estimate this, you can derive this relationship. So if you have a positive coupling, that means K is positive, you have the stochastic noise can even accelerate the flocking. Okay? So the noise acts as a stabilizer. Even negative coupling, if there's no noise, in this case there is no flocking. However, even negative coupling, the noise is large enough, the noise strength is stronger enough, then you still have the flocking. So somehow, for the multiplicative noise, the noise strength helps flocking. Okay. And particle system, you can do similar thing. For example, if your coupling strength, this communication rate has a positive low bound, you can derive this kind of estimate. Here, V is the variance. Okay, variance. So the variance satisfies this estimate. So if coupling strength, if coupling strength is large enough, or for example, this we know that the Brownian motion has at most square root of 2t log t. So if t large enough, this is dominant term. So the right hand side goes to 0 almost surely as t goes to infinity. So you have a flocking. Now the last topic is coupling with fluid. Because so far, how much time do I have? 10 minutes, okay. So far, 15 minutes, okay, yeah. So certainly from this picture, this agent system interact with the fluid, okay, or when the bird fly, also interact with the fluid. So for realistic modeling, you need to consider the coupling interaction between the fluid and the particle system. Okay. So far in engineering literature, they only consider the particle system as a like closed system. Okay, so then for this particle fluid interaction, I'm going to use the kinetic model to describe the particle motion. So you have a Cucker-Smale model. If you use so-called BBG-KY hierarchy from statistical mechanics, then you can formally derive this Vlasov type kinetic equation, and also this derivation can be done rigorously. That has been done by many people here. So from here to here, when n goes to infinity, you can derive this Vlasov type equation rigorously. Okay, it's not a formal. You can do rigorously, and also for viscous incompressible fluid, we use the Navier-Stokes equation. So the question is how to couple this Vlasov equation with Navier-Stokes equations. Okay, I know the liquid crystal, some people use the interaction, also fluid model. So here is the model that we propose. We have a Blasov type equation coupled with a fluid model. So the coupling is through the so-called drag force. Okay, so we use the coupling through the drag force under certain assumptions. So this is your alignment force. We have a drag force. So the drag force is the main mechanism to derive the flocking alignment between the particle and fluid, actually. And you will see later this alignment force accelerate this alignment between the particle and fluid. Okay, so this modeling was motivated by this modeling of thin spray by Bodin and David Led, other people. Okay. Now, so for example, why this model gives you alignment? Okay. For example, let's ignore nonlinear term and pressure. Let's ignore pressure and viscosity. Then the second equation along the particle trajectory can be written like this, right? So this is a flocking force. You see, it's a V minus U. That's the flocking mechanism. So the drag force is responsible for the alignment. So the natural question is, for this proposed model is well posed. Okay, because I'm a mathematician, so this we need to ask first. Or does this proposed model show alignment at least time asymptotically? Because this is the main reason that we introduced this coupling. So the first question for this, in weak framework, weak solution, we can adopt the Bodin's argument, etc. So this can be done. So today I'm just, okay, for example, here's the theorem for strong solution.
Alignment means flocking.
Yeah, so because without coupling, we know that the particles can align, can have the same velocity. Now you couple through the fluid. Then the fluid particle and you have a flocking particle. So the question is how to make a mechanism to make these two different types of particles to align in velocity, right? So the drag force is responsible for that. So suppose you have a unit mass and your initial data in the particle part is bounded, etc. On the smallest assumption, there's some mistake here. Smallest assumption, then certainly you can derive the existence of unique solution, etc. Classical solution also. So this is the tedious part. You have to do energy method, etc. But I'm going to tell you how you can get asymptotic flocking for this model. So to show the asymptotic flocking, we introduce these functionals. Okay. So the first part is the alignment in the flocking particle. The VC is the average velocity of flocking particle. Okay. The second part is the measuring the velocity variance in the fluid part. So this also measures the difference of these average velocities. Okay. So we want to show that these three functionals goes to zero exponentially fast. That means you somehow that exhibit the asymptotic flocking. Of course, we don't know the details mechanism, how, so that's the next question that we can ask in future. Okay, so this you see is the average fluid velocity, because we assume that, yeah, Vc is the average, the particle, the velocity. What you can prove, if initial energy is finite, the viscosity for the fluid is large enough compared to this quantity, you have unfortunately, you have this this quantity sup norm of the particle density in L infinity. Okay, so it's kind of a conditional assumption. Then for any classical solution, you can show that the this E over t goes to 0 exponentially fast. But this assumption is restrictive. But for certain case, you can show that this density is uniformly bounded as long as for any finite time. So that's what you can prove for certain framework. So I'll show you how to prove that. We have a 6 to 1. That's due to some estimate here. Okay. So I want to get rid of this undesirable quantity. So I need a 6 here, 2 here, 1 here to get rid of this undesirable quantity. Okay, so that's the just usual estimate to derive this Grunwald type inequality. Okay, so let me conclude my talk. So the several couplings between the Cucker-Smale model with the noise or fluid or the bonding force are presented, but we didn't show this air show yet. So hope that we want to show in future by using this the particle system to this variety of formation controls in future. Okay, thank you.
Questions?
Yes.